Okay, that time. All right, we're rolling. Any questions? I would say when I was going over number 10 from the master set 22 2 days ago, I was thinking magnetic field when it was actually looking for force. So I apologize for that. So I went over a different problem than what was actually asked. And Ian, if you're wondering what you did force. You did it correctly.
Oh, okay.
All right. Then there's a lab that typically we do at this point, but I always go back and forth on it. It's actually my favorite lab. However, the results anywhere from say 10% error to more typically 100%, or percent difference, I should say. And I'm not quite sure whether it is the student technique which gets really bad results, or just it's all random. So there's another lab that I'm sure Mike has talked about, and I might have made a reference to it, might have made reference, but where the original version of it, 10,000% error was not unusual. And then I've revamped it, so now you should get under 100%, which to me is a victory. But a student gets 100% error might be thinking, wait, I did something wrong. But we're not going to do that lab today. I will at some point take a break and grab the aluminum foil, and we'll do a demonstration, which is the essence of my favorite lab. And what I'm looking for is eluding me. Could just wing it. I think never goes wrong. One of the reasons I'm looking for something specific is that every time I just sort of wing it, I usually end up going in a circle and ending up with something exciting like 1 = 1, which, although it's a true statement, does not really shed much light on what's going on. All right, well, perhaps we'll just go in a circle. There we go. All right, so we have this basic concept that when you have a current flow, I have current flowing through the circuit, and so I have current flowing in this direction, electrons moving in the opposite direction. So what's really happening is that there are holes in here that if I've got an electron, 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 to simplify it into a linear form, there's no place for these electrons to go because there's already an electron in that spot. So really, you've got a hole here, and that electron jumps into that hole, creating a hole here, and then that electron jumps into that hole, that electron jumps into that hole. And so the hole's progressing in this direction as the electrons move in this direction. Now the hole moving in the other direction, sometimes I have seen in presentations in physics, represented by H plus, and it's not, it's more of it's not a particle, it's just, it's sort of like the positive charge moving in that direction. As we've talked about, the electron moving one way is like a positive charge moving in the other direction, usually. But there's this idea that whatever, if I have, at any point along this wire, doesn't really matter what point I pick, whenever electrons flow into it, I have the same number of electrons flowing out of it. I don't have this buildup of charge, statistically speaking, or significantly. Except, let me throw a capacitor into it. We have this idea that whatever electrons flow, whatever current flows into a spot, I have just as much current flowing out of that spot, that current is sort of continuous. I have current flowing in this direction with a capacitor. I have current flowing onto here, and I have current flowing off of there, but there's this gap that we sort of ignored when we were talking about current flowing in equals current flowing out. I mean, with a junction rule, current flows in is equal to current flowing out, but here, I have current flowing in here and current flowing off the other plate, but I don't really have current flowing into here and then current flowing across. But it's not treated like an exception. So we have to figure out how do we actually deal with it. So what I'm going to do here, let's say sort of expand, is I'm going to create a Gaussian surface around it. So imagine you've worked with the parallel plate capacitor lab. I've got a plate here, and I'm just imagining some sort of a Gaussian surface is a virtual surface. I have some surface sort of bounding it. And I need to figure out what actually is conserved. I mean, obviously it's not a charge moving onto the plate and then a charge moving off the plate, but there should be something else that's going on and off. Now I know I have charge built up on this, so I have an electric field that's coming off of it. And if I look at the electric flux, that's equal to, well, whatever the charge on that plate is divided by epsilon sub naught. And this is just the electric field coming off of it. Now again, we're imagining an infinitesimally thin plate here, so my Gaussian surface is hugging it. So even though I have electric field going off in either direction, remember that the electric flux is E dot A. And my area on the end caps is so incredibly tiny, I'm just going to ignore it. Like, imagine if I've got a plate of some thickness, I got 6 sides to it, but the only sides which have any appreciable area is the front and the back. It'd be like, what's the surface area of this? Well, yeah, the bulk of the surface area is here and here. These surface areas we can probably ignore and be pretty darn close. So we will do the same. So this is the part where I sort of start going in circles here. I am going to take one more shot at trying to find it, just so that I repeat myself less. Anyone wants to do the girl from Ipanema for the video, go for it. No one? See a lot of stuff out of place. None of that. Ah, there we go. Definitely in the wrong place. Okay. I don't know why it always throws me. All right, so this is equal to Q over epsilon sub naught. It seems like there should be a 2 in there. Oh, oh. Man. All right, what's wrong with my drawing? The arrows are representing the electric field. I've got part of a capacitor right here. There's obviously some part right there that leads to the battery. What's wrong? Something we talked about. Well, first, it's the reason why there's no 2, but something we talked about when we first talked about parallel plate capacitors.
There shouldn't be any arrows going to the left.
Right, correct. The electric field is completely in the middle. The electric field on the outside of an ideal parallel plate capacitor is 0. So my electric field and my area vector, it's a closed surface, so my area vector is pointing outwards from the dotted line here. Again, this is my Gaussian surface. And then around it on the sides too. So this is just EA. So my electric field is charge over epsilon sub naught times A. Nothing too earth shattering. If we did Q divided by A as the surface charge density, then this basically is the electric field between plates because of the plates. That's not the direction we want to go in. So what I'm curious about is, again, we're talking about current flow. We're talking about charge that's coming up on the plate. Once charged, if the plate is fully charged, then there's no current flowing onto it anymore. So that's not the case we're looking at. We're looking at a case where the charge on the plate is changing. And so if this is my basic relationship here, then the change would be as such. And this delta Q is the change in charge up on the plates. Well, current is change in how much charge passes by or shows up in a certain amount of time, so let's bring time into it. Because the change in the charge and the change in the electric field will occur in the same amount of time. So I get delta E over delta T is equal to delta Q over delta T times 1 over epsilon naught, oops, almost A. Now, sort of reversing something I'd done earlier, this is one of the, I still do that every time, but there's no reason to it. I want A over here, so I'm gonna multiply both sides by A. So I have A delta E over delta T is equal to 1 over epsilon sub naught. Actually, let's go ahead and bring that over also. Epsilon sub naught is delta Q over delta T. And what is delta Q over delta T? Yes. So this is the current that's flowing onto the plate, and what we're making the assumption here is that current flowing into any space is equal to a current flowing off the space. So that's current. I'm going to put a little d down here, and I'll explain the d later. Now here, I've got A times delta E here. A is just the area of the plate. It's a constant, so I can bring it inside the delta or take it out of the delta, either way. I guess if I pull it in, it's called distributing. So we get epsilon naught delta AE over delta T is equal to this current with the subscript D. And what's A times E?
Electric flux.
Yeah. So I have the change in electric flux, and I realize I probably could have cut several steps out of this process. Over delta T times epsilon sub naught is equal to I sub D. So this is not a current because of charge flow. This is known as a displacement current. The current that occurs because charges show up on one plate, leave the other plate, so charges are getting displaced, but there's the gap in the middle. In other words, this is the current that is flowing between the two plates. And it consists of this change in the electric field. So if we look at Ampere's law is that if we go through any loop, that if we do the magnetic field times the change in the length of whatever segment it is equal to mu naught times I. That's Ampere's law. Where this is the traditional current of charges flowing. What Maxwell did is he said, well, this is also a type of current here, so what we should do is actually tack it on. Because we have two different types of current. If we make the substitution here, and distribute, we get the sum of the magnetic field along any closed loop times the length is equal to mu naught times the traditional current plus mu naught times the displacement current, which is epsilon naught delta phi E over delta T. Ampere's law with Maxwell's correction. So this is Maxwell's contribution to what is referred to as Maxwell's equations. And you might be looking at that and going, man, that's just incredible. I can understand all the breakthroughs that came after it. Or you might look at that and say, so what? How does this matter? Well, one, it keeps the idea that, you know, physicists really hate giving up ideas. Thus, the idea that heavier objects fall faster lasted for 2,000 years. But let's put it together with some other of Maxwell's equations and show the impact. By the way, Maxwell did not call them Maxwell's equations, that came afterwards. So we have Ampere's law, we have Maxwell, or Faraday-Lentz's law. The other two is that the electric field times the area is equal to the enclosed charge over epsilon sub naught, and the magnetic field, in essence, the total magnetic flux through any closed surface is 0. I do want to point out this equation right here, this Gauss's law of electricity, is just Coulomb's law. The only difference between Coulomb's law and this is math and definitions. All right, questions up to here before we talk about conceptually the implications and then get into an actual hardcore derivation. Here we go. If I take a charge and I move it from here to here. So imagine I got a charge right here and I just move it. And I'm looking at it from